Okay, so this is a nuclear fission reaction. Of course, the first thing is, how many neutrons. The first order of business is that if this reaction actually works and this is only neutrons, right, that 92 has to equal 57 plus 35. So let's see, 57 plus 35 is 92, right? Okay, and then the mass numbers all have to add up, right? So 235 plus 1 is 236, right? And then if I subtract this and subtract this, right? So if I go 148 minus and 236 minus 148 minus 85, that'll give me the number of neutrons, right? So we're just balancing the mass, right? So 235, 92 plus 10 is equal to 148, 57, right? Plus 85, 35, plus the number of neutrons, right, times 10. Okay. So let's see, what do we got here? 236 minus, I'm going to go minus 148 minus 85. And that's 3. Okay, it has to be 3 neutrons, right? So when I go, this calculation was 236 minus 148. 236 is this, right? Okay, minus 148 minus 85, right? Gave me 3 neutrons. Right? And then you won't be able to look these up in the data table, right? 235 might be in there, but the fission products are all radioactive. They're not on the stable isotope list, right? So I'll give them to you here, and that's just as well, right? So Q value is going to be uranium-235 plus a neutron turns into lawrencium-148 plus bromine-85. Highly radioactive because they have way too many neutrons, right? Remember, this guy has a lot of neutrons relative to the number of protons. So when you split it in roughly half, the fission products have just way too many neutrons, right? Plus 3 neutrons. So now we just plug in the numbers. 235.043923, that's a 4. All right. Plus 1.008665 turns into 147. I think this is the one that was in the IV test, the mock test. 932191 plus bromine, this guy's 84.915608, and then plus 3, 1.008665, whoops, 65. That's a 6. 6. All right, there we go. So I'm going to just take this guy. This side's always going to have less mass by kind of a lot, right? So let's add this guy up, 235.043, 923 plus 1.008665. So this side mass is 236.052588. And then this side mass is 147.932.191 plus 84.915.608 plus 3 times 1.008665. So this side mass is 235.873794. Right, so clearly we've lost a ton of mass here, right? And then I'm just going to subtract. So let's go this guy minus this guy. The mass goes down. So this is plus energy, right? When I figure out how much energy is, it's 0.178794 U's worth of energy, right? That's mass, but we're going to turn it into energy, right? So the Q value is 0.178794 U's. Whoops. And then to convert that to MeV, we multiply by 931.5. And this is MeV per U, right? Okay, so just times 931.5. 166.5. Yeah, 166.5. The next digit's a 4, so it would round down. And you do have, this has 1, 2, 3, 4, 5, 6 sig figs. So if we used a more precise value of this, we could get all the way down to 6 sig figs, right? And of course, you know, this exists in, you know, lots of precision somewhere, right? All right. So in short, for this guy, right, basically you got to figure out the neutrons, right? Figure out how many neutrons you need so that the mass number adds up to the mass number there. Okay, that's it. If the if the proton numbers don't add up, then it's all over. You know, there's something else being created too, which is possible. I'm only going to leave you neutrons left over, so these had better add up. And then once you do that, once you get the neutron numbers, just set up the whole darn old thing here, right? Okay, and then figure out how much energy there is in mass. Multiply by 931.5. In short, find the Q value, right? Okay, yeah. So it's positive. I guess we should say positive, right? It gives off that much energy. I'm not really going to be a nitpicker about you saying positive. They'll all be strongly positive. All right, good enough.